So, final exam prep. We have a practice final. Okay. In comparison to the actual final, and like if we go back and look at your practice exams and compare them to your actual exams, I believe the practice final is a much closer approximation of the actual exam than our practice finals have been, or practice exams have been to the actual exams. Right? That does not mean they're the same questions. That does not mean the wording is the same. So when you go through and look at the practice exam, okay, the practice final, look and say, well, how could this question be changed? Okay, was there another piece that I could have been solving for? Okay, what more information could be provided? What less information could be provided? Okay, so what I would recommend you do is you should complete the practice exam by this Friday. Okay? And that does not mean every question. That means you go through and you answer every question that you think you know. Okay? Any question that you don't think you know, don't do. Just ignore it. Because what you're trying to get a feel for is how you would do on the actual final and establish a way to actually advance forwards. Okay? In this process of going through and taking it, do not use your notes. Don't use the textbook. Don't use a tutor. Okay? This is you. Okay? We're trying to figure out what is stuck in your brain and that you can dump on the final.
When is the final?
May 10th. So it's in 2.5 weeks.
And it's in like 7 o'clock or like 7:30, something like that?
I think it's 7.
It is. So,
Yeah, it's good to know.
Yeah.
it's disgusting.
It's straight off
It
the
doesn't matter
syllabus.
to me. I wake up super early.
I wake up early too, but 7 is pretty early to be here. All right. Any question that you don't think you know the answer to, or you're like, I don't even want to spend the time to trouble to think about this question because it looks like that much trouble, leave blank. Okay? At that point, you should go through and check all your answers with either me or tutors. Okay? I have answers. I will check. Okay? So you can send me an email with all of your questions and what answers. Ideally, it's lists like question 1, 2, can't do 3, so 4, 5, and just your answer choice. Okay? D, A, B, C, F. Okay? I'll go through and let you know what you got wrong and potentially what concept you were missing. At this point, you can go through and look at anything that I said was wrong. You need to find 5 questions just like it. Okay? Because you're in a very dangerous spot. That was a question that you thought you knew. That means when you go through to study, if you don't use this, what's happening? You're not going to study that material, which means when it shows up on the exam, you're going to get it wrong. Okay, so you need to find 5 questions just like it to practice, okay, until you're getting those questions right. That's a lot of questions. That's what you should be doing for every question you ever got wrong. Okay, you need to reinforce how to fix that issue. Okay? After that, if you still have time, rank the blank questions according to a perceived difficulty. Okay, I don't care what your difficulty rating is, but rank them. Okay? Any ones that you think are easy, or you've perceived as easy, solve those first. Okay? Actually, don't even solve those. Find 5 questions similar in content to practice. Okay? Once you have 5 questions that you've practiced, and you're like, okay, I think I get this now, then go back and complete the blank question, and then verify with me. Okay? This is a very iterative process, back and forth, okay? Because you need to figure out what's going on and figure out how to fix those. Okay? As you progress forward through your list of these are now just stupidly difficult, maybe you should decide there's 5 questions that I find stupidly difficult. 5 out of 65 questions is less than 10%. If I get those 5 questions wrong, I have an A on the exam. Do I really want to spend time learning those 5 questions? I'll tell you I want you to do that because I want you to score better because it looks nicer. Okay? But that is your choice. You can decide it's not worth that effort. Okay? That's establishing the bar for yourself. Okay? I know you have other classes. You can decide those 5 or 10, however many you decide, aren't worth studying. That does mean when you get to the final, the actual final, you don't work on those questions. The final has all the questions shuffled around. Okay? The very first question could be something about limiting reactants. It could also be something about sig figs. Entirely different ends of the spectrum as far as both difficulty for students and in order when we talked about it. So when you get the exam, you need to find your questions. Find the questions that you should answer because you are going to get them right. Okay? Or if you think you're going to get most of the tests right, find the questions you're going to get wrong and then don't answer those right away. Guess at least. Make sense? Believe it or not, this is an insanely useful, again, process for how you should prepare for exams and for how you should take exams. Questions about that? This process may not be a bad idea to do for exam 3 between now and Thursday as well. Good? Okay, let's just kind of, because I stepped off the soapbox.
You know what's crazy?
What's that?
Just off topic. My socks match your shirt. Look at that. That's crazy, isn't it?
That's pretty impressive.
That's crazy. All right,
On that note, let's shift gears entirely yet again and go back to our intermolecular forces. Okay, so when we're looking at bonds and forces, we could use these things. So we can look at structures and identify the bonds that are present and then also use that to identify the forces that are present. This allows us to do phase transitions. This addresses issues with vapor pressure, which is an awesome test on the exam, practice exam, by the way. You could potentially look at viscosity, surface tension, solubility, and my favorite out of all of these, reactivity. Reactivity is something you do not need to evaluate for this class. Virtually everything we do in OChem is looking at bonds and forces and how it predicts reactivity. Okay? And the sooner you can come to grips with this kind of interaction and how those things change, the better you can perform in ultimately organic chemistry. I would say you perform better in Gen Chem, but Gen Chem does too much calculations in math that you can't quite get away with just those relationships. Okay? Sorry, misorganized the slides. I thought I shifted. Okay, so I misplaced this one. Extra credit. Okay, everybody wants extra credit. No, sort of not. Really, true, but yes. Okay, dialogues. Should have been doing them. You should have been showing up to the tutoring center. Okay? At this point, we only have 2 weeks left, so you could really only get 2 more dialogues or 2 more large visits to the tutoring center to get credit towards your extra credit. Okay? So if you're in that boat where you're close, do it anyway, because 1, it'll help, and 2, it can potentially get you extra credit. Okay? The next big place for extra credit, there is a survey which some people have already received emails for. Okay? Perfect timing. I love having a survey about my abilities as a teacher right after a horribly crappy exam. Okay? That just warms the heart. Okay? So dump whatever you want into that. That is your prerogative. That is your opportunity to try and fix me or the class. I've tried to give you that opportunity throughout the semester. Some people took advantage of that. Some people didn't. Okay? So within that survey, it is sent to your Maricopa email address. Okay? It is not sent to anywhere else as far as I know. So you have to sign into your Maricopa email address. I can help you with that. And you should get a link. That link is designed specifically for you. You can't click somebody else's link. You have to click yours. When you click yours, it'll open up a window. It'll show you all the courses that you've enrolled in and your opportunity to complete any and all of those surveys.
The second link that has capital, and I don't know why it's bugging me, but it is.
You're right, it is. So here, let's fix it. Is that better? Okay. You do get extra credit for this. Some of your instructors, okay, particularly instructors within their first 5 years at Chandler Gilbert, have been encouraged to offer extra credit. okay, for completing these. So it is a good idea to go through and do it. It is also your opportunity, if you didn't enjoy the experience for any individual class, okay, be it content, instructor, or other students, vent in there, okay? But I did not tell you that or record that for the record, okay? So unload it in there. It's a bunch of multiple choice questions, and then they've got some kind of answer these questions with some words, okay? That is your choice, what words you want to drop in there, okay? As far as I know, I'm the only one that sees them, and I see them, that's actually not true. Okay. When faculty members get evaluated, they're required to upload all of these things, so all faculty could theoretically see these. Okay. And I'm not saying to now temper your word choice, because it's not tied to you. Okay. The only thing it's tied to is your initial entry of that data, and then all gets anonymized. I have no idea who's saying anything. Some people have put their names, then I know. Don't put your name.
You cuss them out.
Okay. The whole point is that it's anonymous. Okay. The other part behind this as well, for reference to other classes, is that not only is it anonymous, they also go through and they don't release this data until well after grades have been entered. Okay. So if you fear like an instructor is going to be like, oh, he got a bad review, he's going to fail everybody in the class. Number one, I don't do that. I find that extremely offensive. Okay? So that shouldn't be an issue. But if you're concerned about it, that's fine. Don't worry, because we don't get to see those evaluations until after grades are submitted. Okay? Kind of makes sense? So when you go through and submit it, this brings to the next part. Okay? They've changed the system around a little bit, so it makes it a little bit more difficult because there's a variety of different things I could go through and do. Once you've finished it, you should see a completion page. Okay? You can screen capture that completion page and then email that to me as an attachment or an image. That's fine. Allegedly, some people will get a confirmation email. You can just forward the confirmation email. Does that make sense? Okay, so what I need to see in that confirmation is the course and your name. Okay. One of the things you should not screen grab, and a couple people have done this, okay, is the evaluation itself. Okay, again, it's supposed to be anonymous. Okay, as you're completing the survey, yes, you could take a screen capture of the survey and your answers to it. Don't do that, because that removes the anonymity. Okay, wait till it's finished. Once it's finished, you can do whatever you want sending me that information. If you send me that, I will give you extra credit. 5 points?
I thought you were going to say percent.
No. Okay. And that potentially can float upwards a little bit, because I think I've got the course out of 1,000, so I might go as high as 10 points. Okay. But anywhere between 5 and 10 points. That is, again, going to get factored in as extra credit. So just like the dialogues, I'll go through and assign grades. Anybody that has this, I'll add those points back in and see what happens. Okay. Once that's done, I'll deal with the dialogues or the extra credit emails. And then I'll also add that in and see if that moves you up. Okay. So if you don't do this, this isn't going to affect your grade. Please do it, because you aren't commenting already, so maybe if it's completely anonymized, you'll be like, screw this guy, okay? Give me something, okay? I do appreciate the comments, though I usually appreciate them if they're more constructive, okay, just in general. Questions about that? There have been some interesting comments. I think the most interesting comment I ever got in an evaluation is that I should wear tighter pants. And I wasn't sure where that was going. Like, because I've got plumber's butt, or like I just didn't know. I was really confused.
Good teacher, but his pants, man. His pants were more big than pants.
Yeah. So. That was too much sharing. I apologize. Melting point and boiling point. So we now have 4 potential exam questions. We want to decide which of those compounds, either 1A or 1B, has the higher melting point. Okay? 2A or 2B has the higher melting point. Okay? We have the context to be able to answer this question based off of ultimately last Thursday's lecture. Okay? So take a look at it, see what you can do. If you're struggling with this, a big hint would be to start with actually question 4, not question 1. It's actually going in reverse difficulty. I don't know why. That's just what I did. 1 is the hardest to answer, then 2, then 3, then 4, 4 being the easiest. I don't know. It's just the way it worked. If you got questions, let's try it this way. Does anybody have questions immediately? And we're like, I need something else to work with. Okay? We'll accept a little hand twirl as something else to work with. When we're looking at melting points and boiling points, okay, what we're referencing is the strength of the force. So I'm looking to melt something. I'm trying to provide enough energy that all the molecules move away from each other. Okay, so I'm breaking the attraction between those molecules. Okay, if I have a really strong attraction between them, how much energy am I going to have to put in? I'm going to have to put in more, which means my melting point will go up. If I have a really weak attraction between those individual molecules, okay, now I don't have to put in as much energy and it'll just break apart. So what we need to go through and do is identify the force for each compound. Okay, and we did talk about that in our previous unit, or our previous lecture on Thursday, about how to address that force. Someone want to toss out where you should be going to figure out that force? Or do you already know where you're going?
Periodic table.
Periodic table is actually not going to tell you the force outright. What we'd be referencing is our summary of our interactions. How do I know I have a London dispersion force, or a dipole-dipole force, or an ionic force? Okay. So I saw a head bob to the left, which may very well have been just head bobbing, but the head bob to the left is actually valid. If I want to determine the force on the right-hand side, ionic, hydrogen bonding, dipole-dipole, or London dispersion, I would need to look to the left. I need to identify what kind of bond is present in my molecule. Okay, so if we go back to the question, we'll write our hints up there, and then we'll let you swing at it. I'm just going to... Let's go ahead and start with 4A and B. Okay, so a couple things of note that we could go through and do. If we look back up at 2B, I started to go through and write out the elements showing up in those formulas because it is very easy to lose track of the elements. So if you can identify what elements are present, that can sometimes help you. So if we move to 4A, we have carbon, we have hydrogen. Please reconnect. Okay, let's try that again. We have carbon, we have hydrogen, and we have oxygen. Okay, and for B, we have carbon, hydrogen, oxygen, and sodium. Okay, so this can, I keep looking at that screen. This can draw our attention to the different elements there, pointing out the fact that these compounds are indeed different. Okay, sometimes that can help, sometimes that won't. For instance, 3 is not going to help us. Okay, so we do indeed have different interactions going to be happening in here. So what we could go through and do would be to draw out their structures, okay, which, believe it or not, you are expected to know already because of our discussion with Lewis. Our discussion on Lewis very rarely touched on actually drawing Lewis structures for more complex formulas, particularly organic compounds. Okay? But that's what you're expected to pick up. Okay, so what we're trying to show is the atom connectivity. We start at the left and we read left to right. Carbon, 3 hydrogens connected to it. Because I need an octet on that carbon, it's missing a bond. So I would show that extra bond. That's where the next carbon comes in, reading left to right. Make sense? Okay, so that would be my Lewis structure. Okay, in our initial discussion, we didn't know the strength of the forces, but to know the strength of the forces, we have to know the bonds. So what bonds are present in 4A? Well, I have a carbon to hydrogen bond, right? Okay, what kind of bond is that? So we could move over to our other side and look at the colors. Notice in the colors, it's only really connecting you the bonds and force. It's not actually telling you what a covalent bond is or what any of the other forces are. Okay. How do we know what bonds we have? The type of element, yep.
So that's polar covalent, right?
We have a carbon to hydrogen bond that is going to be a covalent type, not ionic, but now the question is polar covalent or non-polar covalent. Okay. Well, how do we distinguish those two? This is where we could go back and review the lecture slides from last week, where we talked specifically about how we would identify each of the bonds and their forces. So we had the slide here where on that right-hand side I went through and showed all the bonds and labeled how we would identify them. What was our role for a covalent or rule for a non-polar covalent bond? Same element to same element and carbon to hydrogen. So a carbon to hydrogen bond is by definition non-polar covalent. Okay. How about the next carbon to hydrogen bond? Same thing. And the next one? Same, same, same. So I don't have to stress about those bonds. Those are all going to generate the same type of bond. How about carbon to carbon? That same to same, that's also non-polar covalent. Oh, that's tiny in that corner. I apologize to the side of the classroom. That side of the classroom. Okay. So non-polar covalent bond, there's our NP. Okay. What kind of force would be generated from a non-polar covalent bond? That's where we could now go to our color slide. I apologize to that side of the classroom. Our non-polar covalent bond generates what type of force? A London dispersion type of force. That bond is so strong that it doesn't interact with other molecules. So it generates the weakest of our forces, the London dispersion force. So the non-polar covalent bonds get us London dispersion forces. So we could add that in on our slide on the far right, or your far left. Okay. Did we address all of the bonds in our structure? No, we're also missing the OH bond and officially the CO bond. What kind of bonds are those? Those are, again, our covalent category. It's not same to same, and it's not carbon to hydrogen, which means those are our polar covalent. Polar covalent bonds result in what type of force? A dipole-dipole force. One of the extra things that we have to realize is once we have identified that we have a dipole-dipole force, we must then consider, do I have the opportunity for hydrogen bonding? So first identify dipole-dipole, then I can look to hydrogen bonding. To have hydrogen bonding, what do I need to have? It's a hint. It's the very first word in hydrogen bonding. I have to have a hydrogen. Okay. The next part is this bonding word, which is a horrible, horrible word. It's not a bond. Okay. But I do need a hydrogen actually bonded to oxygen, nitrogen, or fluorine. Do I have that in my compound? Yes. So not only do I have a dipole-dipole force, I also have hydrogen bonding as a force. So of those three forces that I've listed out for this first compound, 4A, which one am I most concerned about? Hydrogen bonding, dipole-dipole, or London dispersion? My melting point, the highest melting point, relies on the strongest force. Which of those forces is the strongest? This is where our chart comes into play. Hydrogen bonding. Hydrogen bonding is the strongest force, so for that compound, I am primarily concerned about hydrogen bonding dictating the intermolecular forces for this compound. Okay? The other ones are still present. They are still there. Okay? But again, if you saw a giant with 3 toddlers running at you, you're probably concerned about the giant and not the 3 toddlers.
I don't know, man. Have you seen toddlers? At least you can talk to them.
That's true. Okay. The strength becomes the larger aspect, or the primary aspect for us to focus on. Okay? When we move to the next compound, we do the exact same analysis. We have carbon to hydrogen, we have carbon to carbon, we have carbon to oxygen. We also have oxygen to sodium. What kind of bond do I have between oxygen and sodium? An oxygen to sodium bond is ionic, which generates which force? Ionic. I know that looks stupid. Right? Also known as electrostatic. Okay. I didn't evaluate any of the other bonds because the rest of those bonds are identical to what we already had. Okay. So I don't want to draw them all out for sake of time. So this compound, the strongest force, is now going to be electrostatic. Okay, so that's going to be the primary force that I want to evaluate for 4b, is the electrostatic force. Which is the stronger force, hydrogen bonding or electrostatic? Electrostatic. Which one's going to require more energy to break the molecule away from other molecules? Electrostatic. So our answer for this one, the compound that has the higher melting point, is B. Make sense? Questions? Okay, can I erase all that stuff at the bottom? Okay, so let's look at a new question. Shouldn't have erased all that because what does 3b generate? 3b is the same as what 4a was. So if we look at all that work, what are we going to say is our strongest force in 3b? We're going to have hydrogen bonding. That is the strongest force in that molecule. I will now also take a look at 3a. The initial analysis that we went through to look for the differences in these, CHO, we don't see an immediate difference in the elements present. So while that is a potential shortcut, how those elements are arranged also becomes really, really important. This is why structure can trump formulas. Okay, so if I drew out that structure, reading left to right, I need an octet around that carbon. I've drawn on my hydrogen, so that means oxygen. Oxygen would have its lone pairs, carbon. That's an H at the bottom, not an A. What bonds do I see in that molecule? Yes, I see carbon to hydrogen. And carbon to hydrogen would be a nonpolar covalent bond, which would lead to London dispersion forces. What bonds do I see in this molecule? Yes, I see another carbon to hydrogen. That leads to nonpolar covalent and London dispersion forces. What bonds do I see in this molecule? Way to preempt me. Yes, let's look at a new bond. The carbon to oxygen. A carbon to oxygen is what type of bond? It is now a polar covalent bond. A polar covalent bond results in what type of force? Dipole-dipole. I have a dipole-dipole, so I should evaluate, do I have hydrogen bonding? Okay, do I have hydrogen? Yes, there is hydrogen. Is the hydrogen bound to oxygen, nitrogen, or fluorine? No. So there is no hydrogen bonding in that molecule. I stop at dipole-dipole. So the strongest force that concerns me in 3A is dipole-dipole. The strongest force in 3B is hydrogen bonding. Which one's the stronger force? Hydrogen bonding, which means which one has the higher melting point? B again. Make sense? So your turn. 2.
What's the strongest bond?
Nonpolar covalent. Right. So our strength continues upwards. So remember, really what our rainbow diagram is a straight line. Okay? All of the possible interactions between any two molecules, or any two atoms. Depending what those atoms are connected to, I may be looking at atoms that are in molecules. So now how molecules interact with each other, I define that as a force. Okay? If I look at two atoms that are now so tightly interacting, I can look at that as a bond. The reason why it's bent into this kind of circle here is that once I've identified the bond, that dictates the type of force. An incredibly strong bond now has no reason to interact with the outside world. So it generates a very weak force. Okay? So it's a classification of which of those atoms, where those atoms are located. Does that make sense? Okay. The thing that gets confusing is what do we use to apply to phase transitions, vapor pressure, and all of that. We aren't looking at the bond, we're looking at the force. Okay? We can't identify the force outright, we'd have to identify the bond first. Okay, so it requires steps. So 2A, what is the strongest force you see in 2A? Okay, nonpolar covalent is a valid answer for the strongest bond, the bond, which is going to generate only London dispersion forces. The strongest force we've got is London dispersion, which happens to be the weakest force. Okay. What about 2B? With that oxygen sitting in the middle, we're getting a polar covalent bond, which generates dipole-dipole. Do I have hydrogen bonding? No. To have hydrogen bonding, a hydrogen must be bonded to the oxygen. It's not. So which has the stronger force? London dispersion or dipole-dipole? Dipole-dipole. 2B has the higher melting point. What do you think? Not too bad? Okay. It is, again, this process of slowly building up. We start at an atom-to-atom interaction, and we classify that bond, we classify the force, and then evaluate, are there other forces to be concerned about? Okay. We have the goal of what we're trying to get through. Last one. What do we have in 1A? So some people are already now jumping to the force, which is good. With practice, you should be able to get that speed. If you aren't there yet, don't stress about it. We have carbon to hydrogen bonds and carbon to carbon bonds, which are all nonpolar covalent, which will result in London dispersion forces. What about the next one? Those are all carbon to hydrogen and carbon to carbon. Those are all nonpolar covalent London dispersion forces. What do you think the answer is? B. Why?
There's more bonds.
There's more bonds. It's not the bonds that are important, but the more bonds we have, the more forces we can generate, or the more attractions we can possibly generate. So it's like comparing one toddler running at you versus 1,000. Okay, 3 isn't enough, but you'd still punt all 3 nicely. Okay, I don't punt toddlers. Which one would concern you more? One toddler running at you, you'd just be happy and give him a hug, or 1,000, you'd probably freak out and run away. Is that better? Okay, so now they're just scaring you. Okay. Love versus, oh my God, I don't have enough love to share. I did a pretty good job with that one, right? Okay. So the amount of the force is also important. The larger molecule has a larger surface area, which means it can interact more with other particles. Okay. So why address this one, or why put this one in here? What you're responsible for is recognizing the different strengths of those forces and ultimately dealing with it at that level. Okay. Can it get more complicated? Yes. This is a case of it getting more complicated. Are you still able to reason through it? Yeah. Right? So it's not that much more difficult to layer that information on. The issue is when you try and look at it outright. Layer information, don't just try and eat it all at once. Okay? Make sense? Like how you eat a cake, one layer at a time.
Is there a time when the one that has the more bonds in this example would have stronger force?
Is there a time where a weaker force but has more of them will overwhelm a stronger force? Yes. Okay, water, shown here, and I'm going to make some abbreviations here, by the way, because I don't want to draw out the whole thing. Water is a liquid at room temperature. Okay, so its melting point, 0 degrees Celsius, keeps it a liquid because it's relatively low. If we take a look at this compound, this is naphthalene. Every one of the points on that structure is a carbon. Okay? And every one of those points has a, well, most of those points has a hydrogen connected to it. So the types of bonds that we have in there are all non-polar covalent. Because it's all carbon to hydrogen and it's all carbon to carbon. Okay, so non-polar covalent, water would generate hydrogen bonding. Naphthalene generates London dispersion. So based on looking at the intermolecular force alone, we would expect water to have the higher melting point. Naphthalene's a solid, which means its melting point has to be higher than water. Why? It's a little bit more complex than just the size of the molecule, but the size of the molecule is the biggest answer there for you. There's now so many more different ways that that molecule can interact with other particles that it actually increases the melting point. So we can see exceptions to this. We have to layer things in carefully to make our comparisons. Okay. By layering in carefully, if we go through and look at what I did within each of these questions, what happens to the size of the molecule in 2, 3, and 4? It stays almost identical. We aren't really changing the size of the molecule. So we do have to keep something constant to make a fair comparison. Okay? So the argument that we could use there, because we've been using toddlers and giants. If you had one giant run at you versus, I don't know, 100 toddlers. Probably stronger than the toddlers, not stronger than the giant, but 100 of the toddlers, I don't know. You have more love that you could give to the toddlers than you have to give to the giant, because we're not punting anymore. It's all about love sharing. Okay? So, phase transitions. Let's drop that back down. Our phase transitions, we'll just talk about this kind of briefly, because we're starting to run out of time. If I look at temperature on the y-axis, and I look at heat on the x. So as I move left to right, what am I doing? I'm increasing heat. I'm putting more heat in. Right? As I move top to bottom, what am I doing? Top to bottom says nothing to do with heat. I'm only affecting the temperature. The top is hot, right? The bottom would be, seriously, cold, right? Low temperatures tend to be cold, high temperatures tend to be hot. So if I pick, say, I don't know, a chunk of ice at minus 40 degrees Celsius, okay? What happens as I add heat? What happens to the ice? Does it melt? So if I add enough heat, what would happen to the temperature? It goes from 40 degrees Celsius to? The temperature goes up. As I add heat, the temperature goes up. Right? We get a nice relationship. Eventually what happens? I get to 0 degrees Celsius. And what happens at 0 degrees Celsius? becomes a liquid. It starts to melt. Do I still have to add heat? So when we hit 0 degrees Celsius, we have no solids, only have liquid. Now at 0 degrees Celsius, we get a mixture of both. Okay? As I continue to add heat, what is that heat doing? It's melting more of the ice. What happens to the temperature? Can I have ice at 1 degree Celsius? That's above the melting point for ice. So no, as long as there's ice present, what happens to the temperature? It flatlines. Until what happens? Until it's all melted. Now what happens is I continue to add heat. It gets warm. And it continues to increase in temperature. Until what? Until I hit 0 degrees Celsius. And what happens at 0 degrees Celsius? That's 100 degrees Celsius. Do what I write, not what I say.
It's like another trick question.
At least I wrote 100 degrees Celsius, in fairness. Turns into a gas. So when I add heat on a stove and it gets to a boil, all of that liquid just goes poof into a gas instantly. No, what happens?
Just evaporate, like.
Some of it turns into a gas, right? Okay, if I continue to heat, eventually all of it turns into a gas. What happens to the temperature of the water? It again stays the same. The temperature of that water will stay constant until there's no more liquid. Now what happens to the temperature of the gas? It continues to go up. Okay, I'm still adding heat. Okay? This is why when you see pipes that say hot steam vent, you're like, 100 degrees Celsius. Yeah, that'd burn me, but it's not going to be that bad. When they're pointing out hot steam, it's probably not 100 degrees Celsius. It's probably 300 or 400 or 500 degrees Celsius. Right? So that when that steam comes out, it's not like, ow, ooh, that kind of hurt. That's like, I can't think anymore because I'm no longer in existence. Kind of a pain. Right? So we can continue to add heat into our gas, and it will continue to rise in temperature. We have to be careful with steam for that reason. Okay, but what we're seeing at those flat lines is we still have to add heat to cause a phase transition. This becomes super important for those of you that move into 151. For everybody else, pretty picture.